Good evening, folks. It is day 19 of Advent of Code. We have about a little under 6 minutes until tonight's puzzles unlock. Thank you all for joining the stream. As always, we're going to be working through these puzzles in C++. If you have any questions or comments, feel free to drop them in the chat, and I'll do my best to answer them. If you have any questions later on watching the stream replays on YouTube, you can feel free to drop a comment there, and I will once again do my best to answer you. So last night we worked on a problem that was about parsing arithmetic expressions that had an order of operations that was different than the one that we're used to. The first one, we had parenthesization, but we had addition and multiplication, had the same precedence, so we just evaluate those left to right, and then we had to modify that and do something where addition had precedence over multiplication, so we did that first. So you can go back and look at the stream replay for that to see how I initially solved it. I cleaned that up a little bit by just moving the language parsing into a separate library here. So we still got this parse full thing, and then this add has precedence parameter controls whether or not add has precedence over multiplication. And then instead, you might recall that last night's solution in parseful, I kind of, parsed everything at one level and then went left to right looking for all of the additions and applied those and then made another pass through and did the multiplications. I changed it so that I think this is a little more clean. I introduced this intermediate function, parse unary or add, which can basically apply either get an expression on the right-hand side in parseful that is either a unary expression like a literal or a parenthesized sub-expression, or an addition that we can add onto and execute immediately. And then after, so we do that on the left side, parse unary or add, and then after we have consumed everything on the left side that's an add, the only thing left is multiplication, and we do that this way. So I think that's a little bit cleaner than having to buffer everything in a vector and scan left to right. Like I said last night, if I were a little more brushed up on yak/bison, writing an actual parser in a parser generator might be the way to go. The other thing I did since we talked last night is I made a super optimized version of day 17 solution. So I timed it out. Day 17 solution, the one that I originally had that I showed you on the screen, took about 6 seconds to complete for part 2. This new version is about 25 times faster. And I did a bunch of different tricks to optimize it. You can see it up in the GitHub repo. Maybe if I still have energy at the end of tonight's stream, I will go into more details about how we did those optimizations. Or I might just do like a supplemental video for the YouTube channel explaining that. But there's a bunch of different techniques here, and we got it down to be really fast using, some things that are just, like algorithmic tricks to make it faster and shortcuts, and also just using some hardware capabilities, using some actual SIMD instructions with SSE or AVX that's available on modern x86 CPUs. That helped us speed up some of the calculations too. But right now we have just a little under 2 minutes until tonight's puzzles unlocks. So let's do our preliminary stuff and get ready to solve them. First thing is, as usual, we'll make a folder for the day's puzzles, and we'll put the little skeleton of part 1 code solution in here. So that's, minimal C++ program, but we almost always need at least my util libraries, check, which I use for assertion, and IO, which I use to read file data. So we'll just put those in ahead of time to save ourselves a little bit of time. We'll make the build file to tell the Bazel build system how to build this binary. We'll specify those dependencies too. Okay, and we'll go ahead and build and run that. Okay, and it successfully compiles and runs and produces no output, which is what we expect. Okay, we have just about 5 seconds until tonight's puzzle unlocks. We'll see how our long journey to go on our vacation goes this evening. Monster messages. Okay. We've got an image of a sea monster. Uh-oh. Send you a list of the rules valid messages to obey and a list of received messages they've collected so far. The rules for valid messages are numbered and build upon each other. Some rules simply match a single character. The remaining rules list the sub-rules that must be followed. For example, rule 012 means that to match rule 0, the text being checked must match rule 1. Text after the part that matched rule 1 must then match rule 2. Some of the lists have multiple lists of sub-rules separated by a pipe. This almost sounds like building up regular expressions, doesn't it? Okay. So pipe just means either of the sequences on either side. There are no loops in the rules. Okay, so the graph of different subrules is acyclic. Okay. Okay. Your goal is to determine the number of messages that completely match rule 0. All right. Let's get our puzzle input here and see just how wild it looks. Okay, so it's all A's and B's, I notice, in the inputs there, and then so we have a number of numbered rules here, and we need to find what completely matches rule 0. Okay, so man, these rules have a lot of subrules. I'm not seeing a whole lot of literals here, though. Oh, 32A, 86B. And that is really it looks like. Okay. And it looks like there's only possibly one pipe in the rules. Are there more than one concatenation in the rules, or no? No, it looks so... So we could actually try and just build up a regex that matches all of these, but this is a simpler language. I think we can actually just build up the a sequence here. Yeah. So let's go ahead and make a class to represent a single rule node. And a rule can be either a sequence of subrules, or multiple sequence. So I guess, yeah. I'm looking through these. There doesn't appear, even though in the example they show us a rule that has 4, 1, 5 all together. I don't actually think that it doesn't look like there's a sequence of more than 3 subrules concatenated together here. But for the sake of yeah, let's go ahead and for the sake of completeness, we'll go ahead and make these rules, so that they can handle, any number of concatenated subrules. So, again, last night I got us on kind of an object-oriented kick, defining a hierarchy of expert classes. I think maybe I want to define a hierarchy of rules classes as well. So we'll say we need a virtual destructor for rule, of course. And we'll have this match and consume. And what this is going to need is it's going to need the, as its first parameter, we're going to pass a string view, which it consumes from, which it tries to match the beginning of and consume from. And we're also going to need a dictionary of other rules, because we aren't strictly going to have rules that are composites contain their children, because it's not strictly a tree. It's a DAG. It's a directed acyclic graph, but the same rule can be a subrule as a child under multiple rules. So, yeah, we will pass in just as a flat hash map. We don't want flat hash set. We actually want a flat hash map. But we will have a map from the integer keys, which are the rule numbers, to rules. And sorry for the heinous formatting there. We just now have it nicely wrapped. And then at the top level, so to check if a rule matches, if a rule fully matches, we'll just do this. We'll just have a match method, which will take a string, and it will return. Well, so we will say and it also has to take that same rule map. But then, to fully match, we have to consume we have to consume the entire string and have none left over. So we return match and consume with that string and that rule map, with the additional check that after it's consumed, that string is empty. So what types of rules do we have? Well, we have literal rule, and it looks like literals are always a single character. So pretty simple. Need to override that virtual destructor. And we need to override match and consume. So we'll just copy and paste these parameters. Const override. And then we can write our very simple implementation. If the string is not empty and its first character equals that target character, then we remove that first character and return true. Otherwise, we return false because it didn't match. So that's a literal rule. Next, we will do concatenation rule, which is a sequence of subrules that have to match one after another. So in this case, we're going to have a vector of ints that represent the subrules that it has to match it against in order. So again, we will have a constructor, and we'll just pass in a span. Just copy those into that vector. Make sure to override that virtual destructor again. Just for those who aren't especially familiar with C++, the reason why we need to override these virtual destructors is that well, they need to be virtual in the first place so that when it's time to actually destroy an instance of these subclasses, like when a unique pointer goes out of scope, we need to know how to actually delete it. And although we're defaulting all of these, which means don't add any special code, we still need to know like how big it is. We need to make sure that the destructors for all the member variables run, and we deallocate all the memory that they might hold. So for concatenation rule, for example, we just overriding and defaulting it makes sure that this vector's destructor also gets run, and we don't leave any hanging memory that used to belong to the vector. So let's do another match and consume for this concatenation rule. So we say for subrule index in subrules, we say if we, well, so first we have to actually look up the gotta find that in the rule map. Well, okay, so that should just be rule iter, because that'll be an iterator. And we want to definitely check that we actually found something, so we check that it's not at the end of the map. And then we try to actually apply that rule. So if we have to dereference if we dereference the iterator, no, I think actually do rule. So we need rule iter. We go to second. That is going to give us the unique pointer holding another rule. And then we will do match and consume for that rule. So we pass it that same string, that same rule map. And so just if we don't match that, we return false. Otherwise, if we get through everything, we've consumed everything, and everything looks good, we can return true. Now, the one thing where things start to Now I'm thinking about an alternation rule where we have that pipe. And it's always one side or the other, but depending on which side got consumed, I'm realizing that the length of the consumed parts could be different, and that could have an impact on things higher up the chain. So maybe instead of passing down just this mutable string, we might need to take into account that there are multiple candidate strings that could exist for an alternation rule. So, this is a little bit tricky. Let me take a moment to think about this. Maybe we make this void, and just if we go down to no candidate strings, then we know that there's nothing more that can be done. Yeah. It makes things a little bit more complicated, doesn't it? The possibility that it could be either or. Now it makes me wonder if maybe we should have just built these into regexes, huh? Well, I'm going to continue with this solution, but yeah, we'll see here. So we'll start with just that one string. Then we'll do match and consume on all of those possible candidate strings, which starts with just one, but we could possibly fan out. If we get to a point where these are all empty, there's no possible match. But we also need to find that one of these has to finally be empty when it is fully consumed. Okay, finally down here, return false if we couldn't find anything that was empty. So now the signature of these is going to change a little bit. So we're going to use remove if here to remove anything from candidate strs that doesn't possibly match this literal rule. I'm beginning to wonder, like, vector might not be the absolute best container for this. Like, maybe a list or something like that might work better if we're going to have to, like, splice this stuff. I might change that, but for now, we'll just say we'll make this little lambda to evaluate the predicate. I mean, right now I'm going to say return false, but that's not obviously not going to be the actual implementation. I just want to put this in here. So we'll say return str dot empty or str dot front does not equal C. And why is it warning us here? Oh, value returned by this function should be used. Maybe there's an absol version of this that is a little friendlier. Because I think that this is actually just going to rearrange things such that we have to actually take the iterator out of it. So then go to the actual end. So we filtered out everything that that couldn't possibly match the literal rule now. But the one thing that we need to make sure of is that everything that remains we actually take the prefix off of. So we will say for each remaining one, we remove that front character. Okay. Concatenation rule. We just need to apply the rules for each of its subrules. Much like we did before. I'm realizing that I didn't want to quite erase all of that because there was some good stuff just for iterating through the map there. So we'll just say void, and we'll copy and paste this candidate stirs parameter. And so we'll go ahead and that'll be rule iter second batch and consume because that will be the actual rule. And I mean, if we ever get to empty, obviously we could short circuit this, but I think, okay, maybe we will. Yeah, we'll leave it alone for now and maybe we'll add that short circuit later as an optimization. So now finally we can come back around to the kind of rule that had me slightly worried in the first place. And that is alternation rules, because these rules can split up into different candidate strings depending on which branch that we take. So alternation rules, can have generally any sort of rule on either. I mean, well, they're either going to be concatenation. They're generally going to be concatenation rules on either side. It looks like, or possibly there's a concatenation on either side of this. And the way that I'm going to choose to represent this is just make it so that it has concatenation rules that aren't in the map that are just directly owned by the alternation rule. So we'll just say that should say explicit. There we go. Need to override the virtual destructor again. Default will do just fine for us. And now we need an implementation of this match and consume rule. So here's where things get tricky, because I realized that we can just push things onto these candidate stirs, but I realized that this could actually be a set now. Although because we're removing stuff from the set, from elements of the set, we'd have to remove and reinsert it. So I think double processing the same candidate strings that might possibly be on either side of an alternation is okay by me. I'm going to let that slide. So should be string view. But this candidate stirs merged for each of the child concatenation rules. We are going to find all of their candidate strings, and we're going to copied from these original candidate strings, and eventually we're going to merge them all together, and that will be the set of candidate strings for the alternation rule, because we can actually fan out, searching either side. And hopefully the memory requirements will not balloon up to something too wild. So here we will just have copy from that original candidate stirs. We will have the child run match and consume on that copy. With the same rule map. And then we will merge those back into candidate stirs merged. So we'll say put those all back together in that vector, and then overwrite that vector. Overwrite the input-output vector here, candidate stirs, with the new merged version on the way out. Okay. So I think we have the right implementations of all of our rules to check strings. Now what we actually need to do is parse strings. So it is parse rules. So we will write a function that builds up our map of rules. So that will be our rule map. And then so we'll say for, I'll actually just use string view. We will split the, let's go ahead and split the string into two parts on either side of the colon first. Definitely going to need vector and string here, and utility for that matter, for remove. Oh, I don't know why we put parse rules down there. I want it to be after all the rule declarations, but yeah, here we go. So to stir split, we have our rule line, and we want to split by that character. So we'll check parts size equals 2. Say int rule IDX, and then we'll parse that with that simple A to I. And then for the rest of the rule, we are either going to, or you know what, we should have the colon and then space as the substring, because that's going to make parsing ever so slightly easier for us. So for the rest of the string, if it contains a double quote, then it's going to be a literal. If it contains a vertical bar, it's going to be an alternation. Otherwise, it's going to be a concatenation. So, what the heck? Let's add little factory methods that can help us parse these. I'm going to make these alternate constructors just because that'll be easier when we're trying to make when we are trying to make unique pointers. So we'll just make these alternate constructors. Yeah. It should be 3, open quote, character, close quote, and then C is going to be equal to the middle one. Okay, so for rule text here, for concatenation rule, we just would split by white space, or just split by the space character, and yeah, we should be good to go. So we'll say so split that rule text by the space character, and then we will parse that actual index and put it on the list of subrules. Okay. For alternation rule parsing, it's a little more complicated, but not that much, to be honest. I realize stubbornly not doing the regular expression way is slowing me down here, but, you know, I felt like doing it this way this evening. So what we'll do is for what we want to do is split that rule text by the string that is a vertical bar with a space on either side. And each one of those will be a possible concatenation rule, which goes into this list of children. So we'll do then children dot and place back subrule text. Okay, so we've got our parsing constructors. Is there a contains method just to search if any character is in a string view? Let's see. Just a sec. Just look up a little bit of documentation here. No, that's proposed for C++ 23, but I think we do not have that yet. Okay. So if if we have the single quote character, then then the rule should be. I'll just put this here. Find it. So if we find that quote character, then it should be a literal. So if it contains a vertical bar, then it should be an alternation rule. And then, of course, otherwise it's going to be a concatenation rule. And now we just make sure that we actually can insert into that map. So we'll do rule map dot try in place. Make sure that was successfully inserted. And then finally return the rule map. Okay. So, going back to the puzzle, your goal is to determine the number of matches that completely match rule 0. All right. Okay. So, to finish up the parsing, what we need to do is actually read the file, parse the rules, get all the strings in, and then check all of the strings, of which there are a fair number, it looks like. So we'll say check argc equals 2. Need to make sure that we get 2 arguments to the program name itself, and then the name of the file to load. Use our read lines from file routine to read all those in. And then we will split by the blank line between them. So use parse rules on, well, we should check that, we get two groups, one group for the rule descriptions and one group for the test strings. So we'll say check line groups size is 2. Then we'll parse rules from the first group. Make sure that we don't get to the end, and then count up the matches for rule 0. So we'll go for okay, I think we have our solution there. To fully build it, we're going to need to put in our dependencies. So we have from absale, we have flat hash map, memory, strings, types. Well, do we really use span? No. If we ever have to do that, I'll just pass it as a vector. So don't really need span, but we do need flat hash map, memory, and strings from absale. So let's go ahead and get some of these. Yep. Okay. And let's put in just the test input from the puzzle to give ourselves a little correctness check before we try it on the full input. So now, let's try and run with that test input and see where we get. Did we not actually print anything out at the end? Oh, we returned it, but we want to actually print it. Make sure we include IO stream for that. There we go. Gives us 2, which is the correct answer for that input. Now let's try it on our actual puzzle input. It gives us 220. Let's see if we are correct, folks. 220. All right. Now on to part 2. You realize the matching rules aren't quite right. To fix them, completely replace rules 842 and 114231 with the following. Oh, now rules do contain loops. List of messages they could hypothetically match is infinite. Need to determine how these changes affect which messages are valid. Might help to start by looking at which rules always match the same set of values and how those rules, especially rules 42 and 31, are used by the new versions of rules 8 and 11. Remember, you only need to handle the rules you have. This would be significantly more... Oh, a formal grammar. Geesh. Without updating rules 8 and 11, these rules... Okay. Ooh boy, this looks kind of tricky, because what once was a DAG is a DAG no longer. Well, let's first copy our part 1 solution over to part 2. And, one thing we can do we could just naively try and apply the same thing, because we do prune down this set of candidates, and maybe we'll stop early enough that we're good? I don't know. I might have to think about that a little bit more, but we shall see. So I'll copy that to get our start on part 2. We'll also copy the build target, since it's going to start off with all the same dependencies. Okay. So now part 2. So what we need to do at the end of parse rules is, as it said, replace rules 8 and 11. So this is going to be 42 or 42 followed by 8. And then we are also going to overwrite rule number 11 with 4231 or 421131. Okay. So let me get the second test input from the puzzle here. Put that in. And just purely as an experiment, let's see how this does with that, and whether it gets stuck in an infinite loop or something. Oh, okay, we seg-faulted. Interesting. I wonder if it's because, we tried to allocate too much memory or something. Let's build with full debugging symbols and try and run it under the debugger and see where that segmentation fault came from. Okay. Okay. Look at the backtrace. Yep. We have a super, super deep stack. So yeah. So that's a little bit what I was afraid of, but I wonder if just adding some early termination conditions might be able to save us from that. So if I Let's see what that does. Not necessarily expecting that to work. Okay. Get a total of 12 messages matched. Let's try that on our actual puzzle input. That early termination condition, if that's all it needed, I'm going to be really jazzed. 439. What do you think, people? Is that it? Is that early termination all we needed? All right! Oh, that might be a I'm not sure if that's a total personal best, but... Oh, man. Just cutting it off when there are no more possible solutions might be all that we needed. Let's look at personal stats on this. Okay. So part 1 of day 15, we ranked a little higher. But other than that, that is one of our overall bests. 582. Oh, man. I feel real good about that. So thank you all for watching this stream. I think that this is a case where we worked through part 1 and, we built up. I think that really having this set of candidate strings was key, because we could split out and look at, okay, what's possible under each branch of an alternation rule, but it also allowed us to stop searching down a path where no matter what was beneath it, we were never going to get any more candidate strings, because we'd already basically reached a dead end in that cycle in the graph of rules. So stopping I guess this is a lesson in quitting while you're behind. When you can't possibly solve the problem anymore, when there's no possible candidate left, stop. So just really, our part 2 solution was remarkably similar to the part 1 solution, just with the addition of those early termination checks, which I was actually thinking a little bit about in the part 1 solution, but those turned out not to be necessary, because as long as the graph of rules is acyclic, you never really have to worry about, you're always going to terminate your traversal of the rules. But when there are cycles, you better find out another way to stop. So yeah, that's our solution for day 19. The code for this solution will go up into my GitHub repository as usual. I'm going to put that on the screen right now. That's github.com/Craig-Chasseur/AOC2020. You can always catch the stream replays on my YouTube channel at youtube.com/spoonboy42. Links for everything is going to be down in the description wherever you're watching this. I just want to say thank you again to everybody for watching the stream. Thanks for having fun with us as we solve these puzzles, and I look forward to seeing you over the next few days as we close out Advent of Code. All right, good night, everybody.